Hello everyone and welcome back to this online NPTEL course. We were learning isotope geochemistry in our previous lecture, and today also we are going to continue more on isotopes and radioactivity. So, in the previous lecture we were discussing what are isotopes. So, as we saw that isotopes are the one which has same atomic number, but variable, and by variable I always mean more, okay, more number of neutrons, that is mass number. And if we see the natural variability of elements and we plot them in this chart where we are having proton in one axis. So, that is basically the atomic number, and we have the neutron number. We will see that this is actually the stability of the elements, that is those elements which have higher neutrons as compared to the number of protons are the ones which are more stable. Okay. So, it up to the atomic number 20 n and n is equal to z, okay, this group is stable, okay, where n is equal to z. But after that mass, okay, after that atomic number, we start forming elements with more number of neutrons in the nucleus than the okay. So, protons, as the atomic number increases, we need more and more neutrons as well. Okay. So, as you see, it is as if it is very steeply increasing as we go with more atomic mass, atomic numbers. Okay. So, the question arises that why are we deviating from this line, right? Why are we deviating from this 1:1 line? Okay. And that is because, as you see, this nucleus, okay, this nucleus is having protons and this is having neutrons. In this tiny nucleus, if the number of protons are increasing, more, what will happen? They are all positively charged particles, right? They are all positively charged particles, and if two positively particles come very close to each other, what will happen? They will have repulsion, okay. They will start repelling each other, okay. So, as we go high on the proton number, to maintain the stability of the nucleus, there is neutrons has to increase, okay, because this is a kind of electromagnetic force, okay. But between neutrons and protons, whatever the force is, that force is called the nuclear force, okay. It is because of this strong nuclear force that the nucleus is stable. It is because of the strong nuclear force that the nucleus is stable. But as the number of protons get increased, the electromagnetic force increases, that means the repulsion increases more than the strong nuclear force. Therefore, more number of neutrons is required to make the atom more stable. Okay. So, we need more neutrons to build up that strong nuclear force to keep the atom stable. Okay. This is the reason that we have this kind of stability diagram. Okay. These elements which are more stable, okay, it is because of this strong nuclear force. So, what we do understand is that not all possible combinations of protons and neutrons result in a stable nuclei. Okay. Can we have more elements here? No, we do not have. it is only in this, as you can see, it is basically like a step. Okay, it is like a little small steps are there. Okay, and they will be, but they are not going to be very stable. So, they will fall back. Okay, they will start decaying and they will be more here. Okay. So, typically it is said an atom is stable when the number of protons is equal to the number of neutrons. But as we go more in the atomic mass, as we reach for more higher atomic numbers, this assumption and this consideration fails. Okay. So, in the nucleus, as I said, that the protons start to repel each other. So, this, imagine it is a subatomic particle and here repulsion is happening. Okay. So, it is apparent that this force which is holding this strong, which is negating this strong repulsion must be extremely strong, because it has to be stronger than this Coulomb electromagnetic repulsion, and that is acting at such small short distances, just imagine subatomic level. So, this is extremely a very strong force. This nuclear force is called a strong force. Okay, it is a kind of a strong force. Okay, and it is one of the fundamental forces of nature. And when we see the stability, okay, we always have to find what is the binding energy therefore. What is the binding energy per nucleon? Okay. So, here we have the binding energy per nucleon in the y axis and we have the mass number. Okay. So, let us see what is this binding energy, how do we calculate that? Okay. It is that energy, this is how we calculate the binding energy. Okay. So, how it is calculated? This binding energy is calculated from the actual weight. Okay. So, this is the actual weight of the atom minus the mass. Okay. So, there will be, okay. So, from the number of protons and the number of neutrons, you will get a theoretical mass. Okay. So, this theoretical mass is my W. This theoretical mass that I will get from the number of by summing the number of protons and the nucleons multiplied by their masses. So, the mass of a proton, mass of a neutron. Okay. So, this you multiply with the proton and the neutron masses, okay. You multiply with that and then you will get the weight. So, that is the weight and this m is the measured mass. And that will be slightly different value, a very slightly different value. So, W minus m when you have, it will be a very small value, but what you do, you multiply that with c square. Okay, you will multiply that with c square. C square is, c is the velocity of light value. Okay. So, if you multiply with that and then you divide with the atomic number, why are we dividing it with the atomic number? Because when we want to get it for per nucleon. Okay. And A is the number of protons plus the number of neutrons, right. So, A is the atomic, so is the number of nucleons, total number of nucleons. So, thus we are going to get the energy which is called the binding energy per nucleon. Okay. And if we plot for the different elements, we see helium has one of the most highest binding energy per nucleon. Okay. Hydrogen is actually very low. So, there is hydrogen, then there is 3 helium, but 4 helium is very high binding energy, very stable, very stable nucleus. it drops a little bit for 6 lithium. Then we have boron, and then it starts again increasing. So, the binding energy increases and it increases up to iron. Okay. You see, the binding energy is one of the highest for iron, but after that it starts to decrease. That means, the binding energy now decreases as we go higher the mass number, the binding energy starts to fall down. So, now after iron several isotopes will come, which is not going to be very stable. Let us look into this kind of energy. So, this force which is called the nuclear force, okay, if it is assigned a strength of 1, let us compare it, because we want to see how if we have some values, it helps us to understand what kind of strength it is. Then the strength of the other forces, if it is electromagnetic force, we can give it a 10 to the power minus 2. So, this is 10 to the power minus 2 and this is 1, and gravity becomes a weak force. Okay. So, gravity actually becomes a weak force in front of the strong nuclear force, and nuclear force, you remember, it is happening at a very short distance. So, that is a very important parameter we have to keep in mind. So, again this binding energy per nucleon is a very important factor to keep the nucleus stable, and it is sometimes directly proportional to the number of nucleons itself. Okay. So, EB, which is a measure of the nucleus stability, those nuclei with the largest binding energy will be the most stable, and often it is seen that the binding energy is directly proportional to the number of nucleons, and it is actually very constant except for certain very light nuclei. For example, 4 helium. Okay. 4 helium was one such exception. So, now we are going to move to radioactivity, that why certain elements is not going to be stable. Okay. So, radioactivity is the emission of particles from an unstable nuclei. So, the nucleus is unstable, right. Certain nucleus is formed which is now no more stable. So, now to go back to its stable state, it will dissociate. Okay. It will form a more stable configuration, and during that dissociation, during that emission, it can actually have 3 kind of emissions. Okay. There can be alpha, beta and gamma. Okay. If it is a alpha emission, what is it emitting? It is emitting 4 helium. Okay. It will be actually emitting a 4 helium. It can have a beta decay, which can be both positive and negative. So, if it is a positive decay, it is basically some positron that is getting emitted. If it is a negative, that means a electron is getting released. Okay. Or some decays can just be energy that is released in the form of photons. So, certain decays can only emit electrons. By emitting these photons, we are just going to release the excess energy and without changing the mass number or the electron number or anything. So, now just come back to this valley of stability that we looked a few slides back. Okay. So, as we said that if we are going to plot the number of, here we are going to plot the number of protons, and here we are going to plot the number of mass number. You can plot either number of nucleons okay, or you can plot the number of neutrons. Okay. So, we can either plot what is called protons, or sometimes we can plot either nucleons or neutrons. Okay. So, for lighter elements, the stable nuclides will always have this. So, you see the color, what the color implies. Okay. So, this is the most stable, the black and white. Okay. So, the black and the white ones, they are the most stable. So, mostly the black ones. So, basically the black ones are the most stable, they are the most stable configurations. The pink ones, as you can see in between, there are a lot of pink boxes. They have a half life which varies between 1 year to 1 billion years. Then we have the blue ones which can vary between 1 hour to 1 year, and we actually have another blue which can have even a shorter lifespan. So, the half life varies between 100 seconds to 1 hour. Certain elements, they have nucleuses which is having extremely small half lives. For example, it can vary from 5 to less than 0.1 seconds. So, that means as soon as it is formed, it starts dissociating. So, just imagine 0.1 second. Okay. So, this is our valley of stability. So, the black one is called the valley of stability, and all the green and the yellow ones, even if they are formed, they will fall back, they will decay and they will fall back here. Okay, they will decay and fall back here. And to return to this valley, they will start emission of particles. So, either alpha or beta or gamma. Okay. They are going to start emitting the particles. Okay. So, we have to understand the stability of these nuclides to understand why they are abundant in nature, why certain elements are more abundant, why certain elements are less abundant. And as you can see from this figure, okay, that iron is one of the most stable element. That is why it is one of the most abundant element also on earth. Okay, it is one of the most abundant element also on earth. All these elements, okay, where you will find basically, so calcium, magnesium, sodium, okay, all the other alkali earth elements, okay, then you have carbon, you have nitrogen, you have oxygen, all these elements, they also have high binding energy and they are very stable. But after iron, all the elements, they will start having this negative slope. Okay, they are having this lower binding energy, and when they are now having this lower binding energy, their occurrence therefore on earth is starting to getting low. Okay. Now, let us see some decays. Okay. What happens if there is a alpha decay? Okay. So, occurs for unstable nuclides with their atomic mass greater than 56, except for 5 helium, 5 lithium and 6 beryllium, which can also go for alpha decay. Okay. They are so unstable that they will go for the alpha decay. Okay. But here, okay, if the atomic mass is more than 56, they will tend to lower their atomic number and also their mass number. Why? Because in alpha decay consists of 2 protons and 2 neutrons. So, if the parent had an atomic number Z, in the daughter atom, that means a decayed product. Okay. So, this will release this and this will form a daughter. Okay. So, that daughter atom will have Z minus 2 atomic number and the neutron number will also decrease by 2. So, the mass number will totally differ by 4, right. So, in this stability diagram, both in this axis also they are coming down and this axis also they are going down. Okay, let us see. So, if I have a 238 uranium, it will decrease 2 neutrons. Okay, so, it is going down this neutron axis and it is also going down this proton axis. Okay, so, it is also decreasing proton wise and also decreasing in neutron wise. So, now it is forming 234 thorium. Okay. So, the decay of uranium becomes 238 uranium forms 234 thorium plus 4 helium, right. And during this entire decay process, how much energy can get generated? So, you calculate what is the mass defect. What is the mass defect meaning? How much energy is lost in between the masses. So, you are subtracting the mass of 234 thorium and 4 helium and you get the mass defect as this much. You multiply with that C square value and you get this much amount of energy that is released for per decay. But if you are talking about in terms of 1 gram of uranium, you can actually see how big an energy this becomes, because it becomes very close to 480,000 kilowatt per hour. Okay. This unit is kilowatt per hour. If I give you an understanding how much this is basically if you have 1000 watt, that is 1 kilowatt, any kind of appliance if you have, and if it is running for 1 hour, okay, that is the energy consumption of that appliance. So, you are having 1000 watt appliance which is running for 1 hour, that is the total energy that is explained by 1 kilowatt hour. Imagine you have 480,000 such appliances you can run from the decay of just 1 gram of 238 uranium. So, this is the principal mode of decay of heavy isotopes such as uranium, thorium. Even this is not very stable. Okay. So, this will also decay. So, thorium they will all decay, 209 bismuth they will also decay. So, these are in between products that they are going to form. Okay, they will form, they will again decay, again they will form, again they will decay. So, in this in this zone there is a lot of instability there. Okay, in this zone there is a lot of instability there. So, it will go on forming, decaying until and unless it reaches a stable nuclei. Let us see how it happens for a beta decay. Okay. So, by decay by emitting a negatively charged beta particle is called a beta decay. Okay. What happens here? The neutron breaks down into an electron and a proton. Okay. The neutron itself will break down into a electron and a proton. So, if you see the parent will start moving up the atomic number ladder. So, the atomic number will increase by 1 because you are adding 1 proton, but you are decreasing the mass of the nucleus. So, the neutron number is decreasing n minus 1. Okay. So, the number of neutron gets decreased, but the mass remains same. Okay. There is no change in the mass. Why? Because that neutron just got converted into the proton. So, here there is no change in the mass number, here there is change in the atomic number, and this is the very preferred when what is happening when there is a lot of extra neutrons is there. So, excess number of neutrons is there, then to remove that you can have the beta decay. Okay. So, this is called the electron decay. Okay. So, the neutron itself will decay to form a proton and an electron. So, it will emit an electron. So, the emission of an electron will be there along with an antineutrino. Okay. This is how it is there, it is called an antineutrino, because this is going to help the conversion of a neutron to a proton, and this does not change in the number of nucleons. Okay. Only the atomic number increases by 1. So, in the decay of 87 rubidium, okay, the number of neutrons just changes. So, it is moving here and it moves like this because the atomic number has increased. So, the proton number has increased. So, it changes. Now, let us see what is a positive beta decay, or otherwise also called a electron capture. So, now here a proton will transform into a neutron with an emission of a positron and a neutrino. Okay. So, here there are more number of protons is there. So, it will just convert its proton to a neutron by capturing one electron. Okay. And there will be emission of a positron and a neutrino. So, here again the number of nucleons does not change. Okay. Here the number of nucleons does not change, only the atomic number decreases. So, the atomic number decreases by 1, okay. The neutron number increases by 1, but the total atomic mass remains the same. And this is the decay mode when there is an excess number of protons. So, very high number of protons is there, it makes the nucleus unstable, and to return back to the stability value, it has to capture one electron, okay. And this conversion is called the beta plus decay or electron capture. Now, how does radioactivity work? So, as you understood that all these in alpha decay, beta decay, electron capture, this is all related to the stability of the nucleus and how how the nucleus is going to become more and more stable, and this is very spontaneous. Okay. This happens because the nucleus itself wants to be more stable. It is now not related to anything like bonding and anything. Okay. So, it is called something called very spontaneous. Okay. It is a very spontaneous activity. And there are two processes, one is called a fission and one is called a fusion. In fission what is happening? It is a breakdown. Fission meaning it is breaking down. Fusion meaning it is getting fused together. So, there are two processes, one is nuclear fission and one is nuclear fusion. Okay. Now, nuclear fission is what, when we are talking about all this radioactivity and radioactive isotopes, it is mostly a very high atomic number element whose nucleus is not stable. It will disintegrate, it will release some particles. So, that is why fission. Okay. In that process it will also release a lot of energy. Okay. And this fission, when it will occur, it is not predictable, it is just the nucleus has to become stable, it can happen anytime. Okay. So, fission activities cannot be predicted, they are very spontaneous, it can happen today, it can happen tomorrow, 10 months back, 10 years down the line, sometime it will happen. So, what we can actually predict is only a probability of decay, that this will probably decay in this many years. So, what we can calculate is what is called as a half life. A few slides back I was talking about the half life of the nucleus. What is the half life? Half life is the average life when we see that the number of atoms of a particular radioactive parent has decayed to half of its initial concentration. How much time does the concentration decrease to half of its concentration, that is called the half life. Okay. And for every radioactive isotope, we have kind of calculated that from experiments, from our theoretical calculations and all that. We have found out what is the half life for each and every radioactive parent. Okay. So, what are we calculating? So, just imagine this experiment. Here we have 20 parent and 2 daughters. Okay. Then we keep it for some time, let it whatever is happening, let the radioactive decay and all that start happen, work up. Okay. After certain time we are going to again measure, and here exactly half number of parents are there now. Okay. So, initially it was 20, now we have 10 parents, and the 20 parents has resulted into 10 more new daughters. So, the 10 new daughters are there, and in the second half life, you just leave it for another half life period, and it again forms from 10 to 5 parents are here, and equally a 5 parents daughters has also formed. So, this kind of experiments has been done, theoretical calculations has been done, and what we have got is we have got understanding of the half life. Okay. We have started to understand what is the half life, and this kind of understanding of what is half life, how much is remaining and all that, this will be forming the basis of radioactive dating. Okay. Extremely important application of all radioactive isotopes is doing dating. Okay. In fact, how old our earth is actually coming from such radioactive dating. Okay. We will stop here in this lecture, and we will continue from this onwards in the next lecture. Thank you.